There are two principal models for the behavior of allosteric enzymes, and we want to consider the concerted model in this lesson. It was first proposed by Monod, Wyman, and Changeux in 1965 and proposes that all subunits within the enzyme change their conformations in concert, that is, simultaneously. All allosteric proteins may adopt the active, or R form, or the inactive T form. In this model, the change between these two forms occurs for all subunits at the same time. In this model, the binding of substrate shifts the equilibrium in favor of the R form. For this reason, the T form predominates in the absence of substrate. Since the enzyme has both T and R forms, there is an equilibrium dissociation constant associated with substrate binding in each form. That is, there is a K sub R and a K sub T. We can define a ratio of the concentrations of the T and R form of the enzymes at equilibrium. This is the L value. We can also define a ratio of the equilibrium constants, which you can think of as indicating the balance between the two, as indicating which is more favored. This is the quantity C, and it is the value of Kr divided by Kt. For an allosteric enzyme that obeys the concerted model, the L value is high, indicating a higher concentration of the T form. The C value is low, indicating the difficulty with which substrate binds in the T form of the enzyme, that is a higher Kt value. There is an equilibrium that exists between the T and R forms. The presence of substrate shifts this equilibrium in favor of the R form, according to Le Chatelier's principle. In other words, as substrate binds the R form and becomes an ES complex, it lowers the effective concentration of the R form of the free enzyme. This results in a shift in favor of forming more of the R form. This model best explains the sigmoidal effects associated with substrate binding. We can demonstrate this by examining the saturation curves as the value of L increases, that is, as the amount of the T form increases. You can see this in the curve on the bottom left, which shows that as the value of L increases, the curve becomes more sigmoidal and shifts from left to right. Let's see what happens to sigmoidicity as the value of C decreases. Look at the curve on the lower right, and you can see that as the value of C drops, that is, as the binding of substrate to the T form becomes less likely, the curve becomes more sigmoidal. Let's see what happens in the binding of activators and inhibitors in this model. As an activator binds in this model, it shifts the equilibrium in favor of the R form. Notice what happens to the saturation plot below. The purple curve, representing activity in the presence of the activator, has become primarily hyperbolic, indicating reduced cooperativity. Inhibitors bind to the T form and thereby shift the equilibrium to favor formation of the T shape. This means that a greater concentration of substrate is needed to shift the equilibrium in the opposite direction to favor the R form. Notice that the green curve in the graph below becomes more sigmoidal and shifts to a higher K1/2 value in the presence of the inhibitor. The important thing to remember from this model is that the conformational change occurs first, then the substrate or effector binds, thereby shifting the equilibrium.